Hello everyone, welcome to the 6th episode of FPGA Limerick. In this episode, we will take a close look at the simulation flow of SpinalHDL. And again, we will use the hello world as an example for demonstration purpose. And the script of this episode has already been posted on the companion blog fpga.pausering.com. Here is our companion blog fpga.pausering.com. Okay, first I would like to discuss the verification methodology. Basically, generally speaking, when it comes to digital circuits, there are mainly two approaches for verification. One is called formal verification. The other is called functional simulation. And in formal verification, there are also two flavors. One is called equivalence checking. The other is called property checking. For the equivalence checking, basically what it does is it can be used to check an RTL against an analyst to see if they are identical, or it can check analyst before route and after route to see if they are identical, or it can be used to validate after an ECO is applied to see the analyst after the ECO is still valid. And a typical tool for this is synopsis formality, which does the job for equivalence checking. And the second flavor, as I mentioned, is called formal property checking. Now, come to think of it, the formal verification is more like a math approach, because basically every digital circuit is nothing but a mapping from input to output, which mathematically fits the definition of a function. Yeah, because it fits the definition of a function, it can use an analytical method to analyze the circuit. So no simulation is needed. And for the formal property verification, what it does is the DUT is treated like a math function whose property is described by SVA. SVA stands for System Verilog Assertion. And as illustrated in this diagram, the tool for formal property verification will use an analytical method to check the DUT against those SVAs and try to find out if there's any counter examples. The SpinalHDL also supports formal property verification, whose details can be found in this link. And we will just leave the rest to the inquisitive viewers, since formal verification is not our focus today. Now let's talk about functional simulation, as it will be our main topic today. As for functional simulation, there are also two approaches. One is called static approach. The other is called dynamic approach. For the static approach, we will prepare the expected input and output beforehand and make them as test vectors. When the simulation is being executed, its output is matched against the test vectors, as illustrated in this diagram. Another approach is called dynamic approach, for which the input is randomized, and the simulation output is compared against a functional model, as shown in this diagram. The driver will generate the random inputs, and the monitor will capture the simulation outputs in the diagram. Now, let's take a look at the simulation flow for SpinalHDL. For SpinalHDL, it can support multiple simulators as its backend. And the main one we will be using is Variolate, as it has the best performance and is the default backend for SpinalHDL simulation. As shown in this diagram, the DUT will be compiled into Verilog and passed on to the Variolate. The Variolate will turn them into C++ code and use GCC to make a shared object. The test bench is in Scala language, and together with the shared object, they will finally produce the waveform dump. Currently, the waveform dump can be in either VCD format or FST format. The VCD format is a text format, and comparing to VCD, the FST is a binary format and is a lot smaller than the VCD, so we would recommend using the FST format for waveform dump. Both VCD and FST can be viewed by a tool called GTKWave. Now let's use our Hello World as an example. The Hello World can be checked out with this tag. I think it's v1.2.3. Okay, let's use the IntelliJ to open it. Okay, let's I think the test bench is in here. It's called an NCO counter sim. Okay. First of all, by the way, I think we need to set up this disable the style check. Otherwise, every line is flagged. Let's do this. Inspection, I remember. And then we make this as a test. Okay, now I think the lint will just skip the test bench. Okay, so this is the test bench. And first of all, please note that although SpinalHDL is built on top of Scala language, the test bench is 100% in pure Scala language, or I would say in the vanilla version of the Scala language. In other words, the test bench is not in SpinalHDL at all. So when we try to get and compare the values from DUT, for example, like say here, when we try to compare, this is the compare thread we try to compare, and see when we get out the simulation output, we use a DUT value. The value will be turned into a long integer, and also if it's that's this one actually is a boolean, and then we will make it into to the Boolean and make it as and then make it as convert it into 1 and 0. So, and let's look at this one. This one in the on our design file, it is for example the counter out. In our design file is here. This is design. See, in the port list, this one is bits, but bits is for SpinalHDL only. So in the test bench, as I mentioned, it is Scala only in the test bench. So Scala does not know the data type as bits. That's why in here we have to make it as too long to convert it into a long integer. Also for the like for this NCO ports, it is reg int force. Actually, you see actually it's a Boolean, and also by default it's force. And also you probably notice the force in the SpinalHDL starts with a capital letter, but in the Scala, the Boolean has a different type. It's spelled as Boolean. So that's why we have to convert this bool in the SpinalHDL into Boolean. And also when we write all the Boolean say true and the false, see we always drive the import or whatever we use, the false starts with a small letter instead of a capital letter, because capital letter true and false is for SpinalHDL, and the small letter true and false is for the Scala. So that's the difference. As I mentioned again, please remember the test bench has to be in vanilla Scala, as being in the 100% pure Scala without any SpinalHDL. That's something we have to remember. Okay, let's move on. Okay, and also we can see the this is the test bench. Actually, it has I would say boilerplated code. So this part is always this is the configure part, because when we do the simulation, we need to also figure out use the same configuration as we do for the DUT. You see, when we generate this is the design. When we generate this DUT, we need a configuration, which is the main config, and the same main config is used here in the with config. And also we need to do the same. And also for the wave, if we can just do without using this, then there will be no wave dump. But if we want to do wave dump, there are multiple ways to do it. I think you can use with wave, which is default, or use with FST or with VCD. I would recommend doing the FST wave, because as I mentioned earlier, it's binary and it's a lot smaller than the VCD. So this is the wave dump, and this is just a compile to set up your DUT and return the DUT, and then the main body of the simulation is here, is in this function, and it's always like this with DUT, to map to something. Now, this is also like set up the period of the clock, and then usually the main simulation will be divided into multiple threads. And here in this hello world example, we have 3 threads, and they all be forked, and then they will be forked. Then after that they will be joined, so they will run in parallel. And here we have 3 threads. One is clock thread. The clock thread is usually set up something to the reset, sync reset, and then it will just wait until everything ends. So see, here is the part where it waits until the comparison is end, and then it do this by clock. So it just starts to the reset and run the clock, and cycle by cycle, so we can keep track of the time. And by the way, this part we don't have to do this. We can just skip. But I would like to keep track of the time. Otherwise, we will just rely on the other two to finish. Because they're gonna join together eventually anyway. At this point. Okay, the other two thread one is called a merger. The merger is not typical in the test vector matching, but I just put it here as an example for sanity check. Basically, it counts the all the clocks and also measure and calculate the true clock frequency of the output clock. This is the comparison, the compare thread. See, what it does is first it reads out a test vector file which we prepared beforehand, and then every time line by line, every clock cycles it check the test vector against the I/O port of this one. See, we have to convert it into a long, and also this one we turn the true and false into 1 and 0 because our test vector is 1 and 0. I think let's take a look at our test vector file. The test vector file is here. There's two columns. For one is for the counter output, the other is for the NCO ports. Yeah, so this part is capture them and use the assert to compare. If something wrong, it will buff and print out the value. Otherwise, it will just keep running until it ends. Then it will set the compare done to true, and then those two threads measure, and the clock thread will also quit if it sees the flag as the comparison flag as compare done flag is set to be true. Okay, so this is the main body of the test bench. Again, please keep in mind that a test bench is in pure Scala language. There's no SpinalHDL in the test bench. So everything, for example, everything like in the force, when you drive it, you have to drive it like this, upon and equal to the whatever the data type should be in Scala, not in SpinalHDL. Okay, now let's run it, see what will happen. Okay, I think the second one is this test bench for simulation. The first one is just to generate the DUT, which we already mentioned in the design flow in last episode. Okay, now it's done. The test bench has finished, and total of like 50k samples is matched. So now we need to look at the wave, since we already said it runs with FST-Wave. Now the wave, it has we need to look at use a tool called GTKWave. This tool, the first time I think you can use it needs to be installed. I think you need to use the MSys. The MSys, you go to MinSys to min W64. I think that's the one, and you do. Let's see, where's our? Okay, I think you need to do this. The first time, if you don't have it installed, you can install on MSys2. We'll say okay, we just say yes. Okay. Now if we use a command and prompt, open the command and prompt, see which GTKWave. Yeah, okay. So let's find out where's the wave dump. The wave dump is in, let's see, the wave dump. If you finish the simulation, the wave dump will show up here in the sim workspace, and then this is the DUT name, and it's test FST. So okay, let's look at it. Hello world sim workspace. Not GTK test FST. Okay. Okay, now we have the waveform, and here's the DUT. We can check out some signals. For example, this one, and this is the counter value, and those are the reset and sync reset. Let's take a look, and I think this is how it starts in the beginning with async reset and sync reset, and the pulse come out, and every time if the value rolls over, yeah, then we have a pause. Okay, that's for the wave, and let's look at the slides, see if there's anything left. Okay, those are the threads. The wave. Okay, I think that's all for today. Thank you so much for watching, and in the next episode we will get hands-on, and we will try to synthesize and place and route the hello world, and download it into our EVA board, flash some LEDs and things like that to show that this is real. Okay, thank you so much for watching, and if you are interested in this episode, or you think this is helpful to you, please subscribe to the channel. Thank you so much for watching, and see you next time. Bye bye.